At the heart of our universe, there's a place that challenges everything we know about the cosmos. Imagine a region of space so vast that it could fit 10,000 galaxies the size of our own. But there is nothing there. Absolute emptiness. A cold spot that astronomers first noticed in space telescope data, and which they still can't explain. This is not just an empty space. This is an anomaly that should not exist according to our models of the universe. The temperature of the CMB radiation there is 70 microkelvin lower than in the surrounding space. Sounds insignificant, but on a cosmic scale, it's a catastrophic deviation that points to something fundamentally strange. When the WMAP satellite first detected this anomaly in 2004, scientists thought it was an equipment error. But subsequent measurements by the Planck telescope confirmed that the Eridan void is real. It stretches 1 billion light-years across and is 3 billion light-years away, in the direction of the constellation Eridanus. What could have created such a giant hole in the fabric of space? The first hypothesis was relatively simple. A supervoid, a huge region of space with an extremely low density of matter. In a normal universe, galaxies are distributed more or less evenly, forming a cosmic web of clusters and voids. But such a void is so large that photons of the CMB radiation passing through it lose energy due to the Sachs-Wolf integrated effect. They are cooling, and we see it as a cold spot. It sounds logical, but there's a problem. Even the largest supervoid should not create such a strong cooling effect. The math doesn't add up. Studies have shown that there are indeed fewer galaxies in this area than expected, but not enough to explain the entire anomaly. Something else is going on there. Some physicists have proposed a more radical idea. What if the void of Eridanus is a trace of a collision with another universe? According to the multiverse theory, our universe may be one of countless bubbles in ever-expanding space. These bubbles sometimes collide, leaving imprints on the CMB radiation. The cold spot may be just such a print, a bruise from a cosmic impact that occurred billions of years ago. It sounds like science fiction, but the mathematics of quantum mechanics and inflation theory allows for this possibility. If this is true, then the emptiness of Eridanus is a window into another reality, proof that we are not alone, even at the level of universes. There's a third hypothesis, even more alarming. Some researchers believe that the cold spot may be due to a topological defect in space-time left over from the Big Bang. Imagine a crack in the very fabric of reality, a cosmic scar that will never heal. These defects, called cosmic strings or textures, could theoretically have formed in the first moments of the universe, when the various forces of nature were separated. What makes the Eridan void truly mysterious is that it challenges a cosmological principle. The fundamental idea that the universe is homogeneous and isotropic on large scales. According to this principle, there should be no special directions or places in space. Everything should be about the same everywhere you look. But the emptiness of Eridanus tells us otherwise. In 2017, astronomers conducted a detailed study of this area, mapping all the galaxies in the direction of the cold spot. They found that there were indeed fewer galaxies there, about 20% fewer than expected. But even this does not fully explain the temperature anomaly. That leaves an inexplicable residue that continues to puzzle scientists. Interestingly, the Eridan void is not the only anomaly in the CMB radiation. There's also the axis of evil, a strange alignment in the large-scale structure of the cosmic microwave background that would seem to indicate a preferred direction in space. Are these anomalies related? Do they point to a fundamental problem in our understanding of the universe? Some physicists go even further, suggesting that the cold spot may be due to dark energy, the mysterious force that causes the universe to expand at an accelerating rate. Perhaps dark energy behaves differently in this region of space, creating a local anomaly in the expansion of space. This could explain why photons are losing more energy there than expected. Imagine looking at a photograph taken 13 billion years ago when the universe was a baby. In this photo, you see a strange dark spot that looks like nothing else. It's like finding a fingerprint on a work of art of nature, a hint that something has interfered with the process of creating the cosmos. The emptiness of Eridanus poses fundamental questions for us. If it is the result of a collision with another universe, then how many such collisions have occurred? Can they happen again? And what does this mean for our place in the multiverse? If this is a topological defect, then what other oddities are hidden in the structure of space-time? There are also practical consequences. If our model of the universe can't explain such a large anomaly, perhaps we need to reconsider the fundamental constants of cosmology. The value of the Hubble constant, the density of dark matter, the equation of state of dark energy. All this may need to be adjusted. In 2021, a group of researchers proposed a new approach. Perhaps the cold spot is not a single anomaly, but an overlay of several smaller voids lined up along our line of sight. Like beads on a string, these supervoids create the cumulative cooling effect we observe. This explanation is more conservative, but it requires an incredible coincidence that several giant voids lined up just to create the observed effect. What's surprising is how much we still don't know about space. We live in an era of precise cosmology, when we can measure the age of the universe to within a few million years. We know the composition of the cosmos, about 5% ordinary matter, 27% dark matter, and 68% dark energy. But at the same time, we cannot explain the giant cold spot in the sky. The emptiness of Eridanus reminds us that the universe is full of surprises. Every time we think we understand the cosmos, nature shows us something that doesn't fit into our theories. And this is wonderful because it is such anomalies that move science forward. Perhaps future telescopes will give us answers. The James Webb Space Telescope and a new generation of ground-based observatories can detect subtle details in the structure of the cold spot that will point to the true cause of the anomaly. Or maybe we'll need an entirely new physics, a theory that unifies quantum mechanics and general relativity in a way we can't yet imagine. In the meantime, the emptiness of Eridan remains one of the greatest mysteries of modern cosmology. It hangs there in the sky, cold and dark, a silent reminder that the universe is much stranger and more wonderful than we can imagine. And somewhere in this emptiness may lie the key to understanding the very nature of reality. When astronomers look at the Eridan void, they don't just see the absence of galaxies. They see a puzzle that touches the very foundations of our understanding of the cosmos. Each new sighting adds details, but the picture only gets stranger. Think about the scale. 1 billion light years across. Light, the fastest thing in the universe, travels through this void for 1 billion years. During this time, civilizations can arise and disappear thousands of times. Stars are born, live, and die. But in the void of Eridanus, all this is dramatically less. The interesting thing is that emptiness is not a vacuum in the literal sense. There's still matter out there. It's just about 30% below the average for the universe. That may seem like a small difference, but on a cosmological scale, it's huge. This is the difference between a thriving space metropolis and a desert. Imagine looking at a map of the night sky from the center of this void. Instead of the thousands of galaxies we see from Earth, you would see only a pitiful handful of points of light scattered in the ocean of darkness. The sky would have been much, much darker. The universe would seem more lonely, more empty. Until recently, such a civilization might not have known that other galaxies existed at all. But why do such voids form at all? The answer lies in the early history of the universe. Immediately after the Big Bang, matter was distributed almost perfectly uniformly, with tiny quantum fluctuations in density. These fluctuations, amplified by cosmic inflation, were the seeds of the entire structure we see today. Regions with a slightly higher density attracted more matter under the influence of gravity. They became even denser, forming galaxies and clusters of galaxies. And regions with a slightly lower density lost matter, which leaked to denser regions. Over time, these non-dense areas grew, becoming giant voids in the cosmic web. This is a natural process, and there are voids all over the universe. But the void of Eridan is too big and too empty, even with this mechanism. Computer simulations of the evolution of the universe show that such a gigantic structure is highly unlikely. Not impossible, but so rare that we shouldn't have found it in the observable part of space. This leads us to a statistical problem. If the Eridan void is so improbable, then either we are extremely unlucky and live in a very atypical part of the universe, or our models are incomplete. Most scientists are inclined to the second option. Somewhere in our equations, there's a missing factor, an unknown variable that makes such structures more likely. One possibility is related to primordial gravitational waves. During cosmic inflation, in the first fractions of a second after the Big Bang, space-time expanded faster than the speed of light. This expansion should have created ripples in the very fabric of space-time, gravitational waves on a colossal scale. These waves could have left imprints on the distribution of matter, creating unusually large structures. Another intriguing possibility has to do with dark matter. We know that dark matter exists because of its gravitational effect on ordinary matter and light. But we don't know what it is. Most models suggest that it is cold, dark matter, particles that move slowly by cosmic standards. But what if there are different types of dark matter with different properties? It is possible that the Eridan void region is dominated by a special type of dark matter that interacts in a different way. Or maybe something happened in the early universe that changed the local ratio of dark matter to dark energy. These ideas are speculative, but they show how wide the range of possibilities is. There's also a philosophical aspect to this mystery. We're used to thinking of the universe as something understandable, governed by laws that we can discover and write down in mathematical language. But what if the reality is fundamentally stranger? What if there are phenomena that cannot be fully understood within the framework of our mental models? The emptiness of Eridanus makes us think about the limits of scientific knowledge. On the one hand, we have incredibly precise tools and sophisticated theories. On the other hand, we encounter phenomena that these theories cannot explain. This tension between knowledge and ignorance is what makes science exciting. It is also interesting to think about how future generations will view this mystery. Perhaps 100 years from now, students of cosmology will wonder that we ever found the emptiness of Eridanus mysterious. The solution may turn out to be elegant and obvious in retrospect, or maybe it will remain one of those deep mysteries that point to the limits of human understanding. When we look at a cold spot in the constellation Eridanus, we are looking back in time. The light we see began its journey billions of years ago, when the Earth did not yet exist, when our sun was not yet born. This ancient light carries information about the state of the universe in those ancient times, encoded in its temperature and polarization. The CMB is a kind of children's photograph of space, a picture taken when the universe was only 380,000 years old. Up to this point, the cosmos was opaque, filled with plasma that light could not pass through. But when the universe cooled enough, electrons and protons combined to form hydrogen atoms, and light was able to travel freely. This moment is called recombination, and it was then that the CMB radiation appeared. Since then, it has traveled through expanding space, cooling and stretching until it became the microwave radiation we see today. And there's a strange dark spot in this ancient photo that shouldn't be there. What makes this situation even more intriguing is that the emptiness of Eridan is not just an academic puzzle. It has real implications for our understanding of fundamental physics. If we can't explain this anomaly, then perhaps we need to revise our models of gravity or inflation or even the Big Bang. Some physicists have suggested that the cold spot may be due to modifications of Einstein's general theory of relativity. This theory works great in most situations, but we know that it can't be the final word because it's incompatible with quantum mechanics. Perhaps on cosmological scales, gravity works a little differently, and the void of Eridanus is a hint at this modification. There's also the possibility that the anomaly is related to the initial conditions of the Big Bang. Most cosmological models assume that density fluctuations in the early universe followed a certain statistical distribution called Gaussian. But what if there were non-Gaussian components, rare abnormalities that created unusual structures? These non-Gaussians could be the signature of exotic processes during inflation. Perhaps the inflation field interacted with other fields in ways that we don't account for in standard models. Or maybe inflation itself occurred unevenly, with local variations that left imprints on the structure of the universe. One of the most fascinating aspects of the Eridan void is that it makes us wonder about the nature of space itself. We're used to thinking of space as an empty container in which things exist. But modern physics tells us that space is a dynamic entity that can curve, expand, and even tear apart. In quantum field theory, even empty space is bubbling with activity. Virtual particles are constantly appearing and disappearing, borrowing energy from the vacuum for brief moments before annihilating. These quantum fluctuations in vacuum are real. We can measure their effects in laboratories. But how do they behave on the scale of 1 billion light years? Perhaps the Eridan void is the region where the quantum nature of space manifests itself at the macroscopic level. Maybe there was a rare quantum fluctuation on a colossal scale that created a local anomaly in the structure of space-time. It sounds unbelievable, but quantum mechanics is full of incredible phenomena that are nonetheless real. Another possibility involves cosmic strings, hypothetical one-dimensional defects in space-time. Imagine a crack in an icy lake. Only instead of ice, it is the fabric of reality itself. These strings are incredibly thin, smaller than an atomic nucleus in width, but they can stretch for billions of light years. And they have a colossal mass. A kilometer-long piece of cosmic string can weigh more than the Earth. If a cosmic string passed through the region that became the Eridan void, it could have affected the formation of the structures in such a way that it would have created the observed anomaly. The string's gravitational field curves the space around it, creating a lensing effect and affecting the motion of matter. Over time, this could lead to the formation of an unusually large void. The problem is that we have never detected a cosmic string directly. They remain theoretical objects, predicted by some theories, but not confirmed by observations. If the void of Eridanus is indeed connected to a cosmic string, it would be one of the greatest discoveries in physics. There's also a more mundane, but no less interesting explanation. Maybe the cold spot is just a statistical fluctuation, the cosmic equivalent of tails falling 20 times in a row when a coin is tossed. This is unlikely, but not impossible. In a large enough universe, even extremely rare events must occur somewhere. This idea is related to the anthropic principle. If the universe is infinite, or if there's a multiverse with an infinite number of universes, then there must be a region with an anomaly like the Eridan void somewhere. And we can observe it simply because we exist in the part of reality where it is. This is not an explanation in the traditional sense, but it is a reminder that rare events become inevitable on a sufficiently large scale. It is interesting to think about how the discovery of the emptiness of Eridanus fits into the history of cosmology. Each generation of astronomers has made discoveries that have expanded our understanding of the scale of the universe. Galileo saw that the Milky Way is made up of stars. Hubble proved that nebulae are distant galaxies. Penzias and Wilson discovered the CMB radiation, confirming the Big Bang theory. Each of these discoveries showed us that the universe is bigger and more complex than we thought. The emptiness of Eridan continues this tradition. It shows us that even when we think we understand the large-scale structure of the cosmos, there are still surprises out there that challenge our theories. What amazes me is the elegance of how we can study this phenomenon. We can't send a probe to the Eridan void. It's billions of light years away, and even traveling at the speed of light, it would take billions of years to get there. But we don't need it. The light that has passed through this area carries information in its properties. By measuring the temperature and polarization of the CMB, we can reconstruct the history of this region of space. It's like archaeology, only instead of digging in the ground, we dig through time, using light as our shovel. Each photon is a messenger from the ancient past, and if we learn to read it correctly, it will tell us its own story. Modern telescopes allow us to do this with incredible precision. We can measure temperature differences in millionths of a degree. We can map the structure of the CMB with a resolution that would have been unimaginable just a few decades ago. And with each new sighting, we add details to our map of the cosmos. But the more we learn, the more questions arise. Why does the cosmological principle, which works so well in most cases, seem to break down in the case of the Eridan void? Are there other anomalies that have not yet been discovered? And what do these anomalies tell us about the fundamental nature of reality? Some physicists have suggested that we could live in a holographic universe, where all information about three-dimensional space is encoded on a two-dimensional surface. It's a radical idea, but it stems from serious theoretical work in quantum gravity and string theory. If true, anomalies like the Eridan void could be glitches in the holographic projection, places where information is encoded in a non-standard way. This may sound absurd, but remember that many of the things we now accept as fact once seemed absurd. The idea that the Earth revolves around the sun was contrary to common sense. Quantum mechanics, with its uncertainty principle and wave function, seemed insane even to its creators. But reality does not have to correspond to our intuitive ideas. The emptiness of Eridanus also raises questions about the nature of time. When we look at a cold spot, we're looking into the past. But it's not just the distant past. It's the early past of the universe, a time when the laws of physics may have worked a little differently. In the extreme conditions of the early universe, at unimaginable temperatures and densities, processes could occur that cannot be reproduced or even fully understood today. Maybe the void of Eridan is a fossil from that era, a trace of an event that occurred when the universe was only a few seconds old. Perhaps during the phase transition, when one of the fundamental forces separated from the others, there was a fluctuation that created the seed for a future giant void. There's also speculation about a connection with black holes. Some theorists have suggested that primordial black holes could have formed in the early universe, objects that arose not from the collapse of stars, but directly from density fluctuations after the Big Bang. If there were fewer primordial black holes in the Eridan void region, this could affect the formation of galaxies and create the observed underdensity. Or, conversely, maybe there was a supermassive black hole or a group of such holes, which by their gravitational influence created a region with a reduced density around them. These holes could have evaporated through Hawking radiation, leaving behind only a gravitational imprint in the structure of space. Hawking radiation is itself one of the most amazing predictions of theoretical physics. The idea that black holes can evaporate by emitting particles unifies quantum mechanics, thermodynamics, and gravity in a way that is still not fully understood. If primordial black holes did play a role in the formation of the Eridan void, it would be proof that quantum effects can have macroscopic cosmological implications. Think about the time scale. The universe is now about 13.5 billion years old. The void of Eridanus has been forming for most of this history. This is not an instantaneous event, but a process stretched over eons. Matter was slowly draining out of this region, pulled by the gravity of the surrounding denser regions. Over time, the underdensity grew, the void expanded, becoming the cosmic desert we see today. But even when calling it a desert, we must be mindful of the context. There are still millions of galaxies in the Eridan void. There are just fewer of them than there should be. From a human point of view, it is still an unimaginably rich, matter-filled space. But by cosmological standards, this is really a void, an anomaly in the distribution of matter. It is interesting to imagine what astronomy would be like if humanity had evolved on a planet in the center of the Eridan void. Ancient astronomers would have seen far fewer galaxies in the sky. Perhaps the discovery that the universe is filled with galaxies would have come much later. Or maybe they would have thought longer that they were living in a uniquely empty cosmos, unaware that they were in an anomalous region of a larger, densely populated universe. This raises a philosophical question about a cosmic perspective. Our understanding of the universe is inevitably colored by our location in it. We are on the outskirts of an ordinary spiral galaxy in a typical region of space. But what if we lived in a less typical place? How would this change our understanding of cosmology? The anthropic principle says that we are necessarily in a part of the universe that can support life. But within this limitation, there is a huge variety of possible locations. The Eridan void reminds us that the cosmos is not homogeneous, even if it is statistically homogeneous on large scales. Returning to the possibility of a collision of universes, this idea opens up mind-boggling prospects. If our universe did collide with another, then what properties did that other universe have? Did it have the same physical constants? The same laws of nature? Or was it a completely alien reality with different types of particles, forces, and even dimensions? String theory predicts the existence of many possible universes, each with a different configuration of folded extra dimensions. The number of possible configurations is so large that physicists call it the string theory landscape, a metaphorical landscape with 10 to the 500th power of different valleys, each representing a possible universe. If the collision did occur, then another universe could be one of these alternative configurations. The trace of the collision, imprinted in the relic radiation, would be a window into another physical reality. It's like finding a fossil of a creature from a parallel evolution, proof that other paths of development are possible. But let's get back to more mundane explanations. One of the problems with exploring the Eridan void is that we only see it from one angle, Earth. We can't fly around it, we can't look at it from different angles. It's like trying to understand the shape of a mountain by seeing it from only one vantage point. Astronomers try to get around this limitation by using a variety of observation methods. They study not only the temperature of the CMB, but also its polarization, the distribution of galaxies, and gravitational lensing. Each method gives a slightly different perspective on the structure of this region of space. Gravitational lensing is particularly interesting. When light from distant objects passes through a region of high mass, its path is curved by gravity, just as light is bent when passing through a lens. By studying how light from objects beyond the Eridan void bends, we can map the distribution of matter within it, including invisible dark matter. These studies have confirmed that the Eridan void does indeed have less matter than expected, but they also showed that the distribution of matter there is not quite ordinary. There are strange patterns, asymmetries that hint at the complex history of the formation of this region. One aspect that is often overlooked is the role of dark energy in all of this. Dark energy is a mysterious force that makes up about 70% of the energy of the universe and causes the cosmos to expand at an accelerating rate. We know it exists because we can see its effects, but we have no idea what it really is. The simplest model of dark energy is the cosmological constant, a number that Einstein added to his equations and then called his greatest mistake. But it turns out that the cosmological constant is real, it just has very little significance. The problem is that quantum field theory predicts that its value should be 10 to the 120th power of what is observed. This is the worst prediction in the history of science. Perhaps the emptiness of Eridanus is connected to this mystery. What if dark energy isn't exactly constant throughout space and time? What if there are local fluctuations in its density or properties? Such fluctuations could affect the rate of expansion of space in different regions, creating anomalies like a cold spot. This leads us to the idea that the constants of physics may not be as constant as we think. For most of the history of physics, it was assumed that the fundamental constants, the speed of light, the Planck constant, the charge of the electron, were the same everywhere and at all times. But some theories allow for the possibility that these constants may vary in space or change slowly over time. If so, then the Eridan void may be a region where the physical constants are slightly different from ours. This does not necessarily mean that the laws of physics are different there. The laws may be the same, but with slightly different parameters. It's like the same mathematical formula, but with different numbers inserted into it. Finding such variations would be revolutionary. This would mean that the universe is even more diverse than we thought. It could also help explain the fine-tuning problem. The mystery of why the constants of physics have the exact values that allow complex structures like stars, planets, and life to exist. In a multiverse with variations in the physical constants, different regions will have different properties. Most regions will be uninhabitable, but in rare areas where the constants happen to be suitable, observers can evolve. We're necessarily in one of those areas, because otherwise we wouldn't be there to ask these questions. But even in a habitable area, there may be anomalies like the Eridan void, remnants of boundaries between regions with different constants, or traces of processes that occurred during the establishment of these constants. There is also the question of causality and the event horizon. At the moment when the CMB radiation was emitted, the different parts of the universe could not be causally related to each other. They were outside each other's event horizons. However, the temperature of the CMB radiation is remarkably uniform in all directions. This is the horizon problem, and it is one of the main motives for the theory of cosmic inflation. Inflation solves this problem by assuming that all observable parts of the universe were once in causal contact, before inflation inflated them to enormous proportions. But the Eridan void is so large that it raises questions about how such a large-scale structure could have formed. If the anomaly arose before inflation, it must have been a tiny quantum fluctuation that inflation has stretched to cosmic proportions. If it arose after inflation, we need a mechanism that can create such a large structure in an expanding universe. Neither option is easy, and both pose difficult questions. Thinking about all this, I'm amazed at how much we can learn just by looking up at the sky. Every photon that reaches our telescopes carries information. Its energy tells us about the temperature of the source. Its wavelength, altered by cosmic expansion, tells us the distance. Its polarization tells us about the magnetic fields and scattering processes through which it has passed. By collecting billions of these photons and analyzing them statistically, we can reconstruct the history of the cosmos. This is an incredible intellectual achievement, the fruit of centuries of scientific progress. From Newton's laws of motion to quantum mechanics, from spectroscopy to cosmology, they all come together to give us a picture of the universe. And yet, despite all our progress, all our telescopes and equations, the Eridan void remains a mystery. It's a humbling reminder that the universe will always be one step ahead of us, will always hold secrets that challenge our understanding. Perhaps this is the true beauty of science, not in the final answers, but in the constant journey of discovery. Each solved riddle opens up new questions. Each answer leads to a deeper level of misunderstanding, which requires even more sophisticated tools and theories. The emptiness of Eridanus is not just a cold spot on the map of the CMB. This is an invitation to think deeper, to observe more closely, to question our assumptions. It's a window into the processes that shaped the universe billions of years ago, and perhaps into a reality that exists beyond our own. When future astronomers look back at our time, they may be surprised that we found this anomaly so mysterious. Or maybe the Eridan void will be one of those great epic-defining questions, a catalyst for an entirely new physics that we can't even imagine yet. There, in the direction of the constellation Eridanus, at a distance of 3 billion light-years, there is a gigantic void. Cold, dark, almost lifeless by cosmic standards. But in its emptiness, it tells us something important about the nature of reality. It whispers to us that the universe is still full of wonders, that the boundaries of our understanding are not walls, but horizons beyond which lie new discoveries. And as we stare into this abyss, trying to unravel its mystery, it looks back, mute and mysterious, keeping its secrets in a cold light that has traveled for billions of years to reach our eyes. The emptiness of Eridanus awaits. She waits until we are wise enough to understand her message.